Hi everyone. I know probably it's a bit annoying to see another person from MIT, so hopefully I'll try to make this as interesting as possible. It's a topic I find very interesting, and I hope to convince you of the same. Um, so I want to begin with why one should care about strong light matter interaction, and the reason we care about it is because conventionally in the classical world, most of the interactions between light and matter are weak. And one way of seeing this is if we were to shine light on a block of a solid or something. The spot size of this flashlight, for instance, is maybe centimeters squared or millimeters squared at best. And the atomic cross-section to interact with an electromagnetic wave is on the scale of a wavelength squared, which is orders of magnitude smaller than this millimeter squared spot size of the beam. So that means that it's very improbable that a single atom will interact with a given photon in the flashlight. And so that turns out to mean that, conventionally we have very weak interactions between photons and atoms and weak interactions between photons and themselves. So there's this really nice diagram that shows kind of the different regimes of light matter interaction. And generally in the classical realm, we're at the bottom part of this diagram where we either have linear optics, or if we drive our atoms at very high intensities, we can get nonlinear effects. But really cool stuff starts to happen when you can actually crank up the interaction strength per photon. So photons start to interact strongly with atoms and with themselves. And that's when you start to get very interesting quantum effects. So it's my belief that open challenges in photonics really rely on being able to increase the strength of light matter interactions. And one of the challenges I want to focus on is generating quantum states of light. And I want to convince you that these are important from both a fundamental physics point of view, as well as for applications in quantum sensing and quantum information. The second topic is ultra-strong coupling. It turns out that when light and matter can couple very strongly together, it turns out you can actually change the physical and chemical properties of matter. The third topic is being able to interact free electrons with nanophotonic structures to generate coherent sources of light across the electromagnetic spectrum. And the last topic is to harness multimode nonlinear optics to actually generate entangled quantum states of light. And given that I have 5 minutes, I'm going to focus on this first topic here, although I'm happy to discuss the other three. And I want to emphasize here that these are all very interdisciplinary and highly interconnected problems. And they are key avenues to combine theory, computation, and experiment. So quantum states of light, why are they important? Well, they're quantum because there's no classical analog. So in the fundamental theory of quantum electrodynamics, which describes how atoms and light and matter interact, the very fundamental state are these so-called Fock states, which are number states of light. So if I had a state of light in my hand where I could say it had exactly 100 photons, that would be an example of a Fock state. There's no classical state of light like that. The best case we can do is a laser, which has a coherent state, which has some intensity noise that follows a Poissonian distribution. And these Fock states are very important from both a fundamental point of view as well as from a practical point of view, because it becomes possible to actually detect signals that would otherwise be lost in shot noise. And you can also use these Fock states for quantum computing protocols where you can actually do operations on photon number. But there's no good way to produce quantum states of light like Fock states with classical intensities, with hundreds or even millions of photons. So I want to quickly give an overview of the method that I and collaborators developed to do this, and it's the so-called Fock laser. So I mentioned how conventional lasers produce coherent states of light. And the way they work is there's this balance between gain and loss, and the laser operates at the intersection of the gain and loss, as you can see in the panel B. Now, the idea in a Fock laser is we're going to actually try to engineer the loss to make it sharply rising. And I'll explain in a moment how we can do that, but it turns out, if you imagine that, if we perturb away from the steady state point where gain and loss intersect, the sharply rising loss will immediately pull you back towards the steady state point, and consequently, if you went on the other direction, the difference between gain and loss will pull you back towards the steady state. So intuitively, this has the effect of squeezing your photon number distribution. So instead of a coherent state, you now get a state that's squeezed very tightly in intensity noise. So this can generate a near Fock state. And what we've been able to show is that you can get over 12 decibels of broadband squeezing, and I'm currently working on using this similar phenomenon to generate other quantum states of light. And since I have 15 seconds left, I won't explain how you generate the sharply rising loss. I can explain it in the questions. But as I mentioned, I will skip the other, that. Um, and so, I just want to end by saying that I truly believe that the strong light matter interactions that I'm really interested in is an avenue to combine not just photonics, but also topics from machine learning, which I haven't talked about, and material science. And it's truly an interdisciplinary field and one that I'm really excited about. So I just want to acknowledge the support of my collaborators, Marin Soliacic's group at MIT, Donnie Keithley's group at MIT, and Frank Coppens, who's at the Institute for Photonic Sciences in Barcelona. Thank you all for your attention.
Hi, thanks for the nice talk. I'm wondering if there's, besides like just sub-Poissonian photon number statistics, like maybe it's a delta function, can I also like think about what a near Fock state looks like in quadrature space? I guess like a coherent state you would think is like a Gaussian distribution.
Yeah, for sure. So people generally generate squeeze states using like a nonlinear crystal, and so like if you're thinking about it in quadrature space, plotting like the coherent state real part and imaginary part, a Fock state would correspond to like a ring, because your phase is in the limit of an absolute Fock state. You have absolute phase uncertainty, so it would correspond to a ring in that quadrature space at a very well-defined magnitude. And if you had a phase squeeze state, which is the opposite, then you would have like perfectly defined phase, but completely undefined amplitude. Does that help?
Thank you.
Yeah. All right. Thank you.